I think we can start. Thank you for showing everyone. My name is Shubham and I will be taking this session. Uh, so we will go over some examples in this session that will help you solve some of the questions. Maybe it will be helpful for your next homework as well. Let's go over the logistics first. I think the homework 2 is already published on Piazza. You can find it on Canvas. And the deadline is, I think, April 20. It is, I think, next Thursday. We have published our availability on Canvas. Like if you're interested in one-on-one sessions with the TAs or tutors, feel free to register for that. And during this presentation, if you find any difficulty in understanding anything, feel free to interrupt me anytime you want. So as we saw in the previous lecture, there are two ways to solve the graph problems. One is with reduction and one is with modification. So as Professor Miles have explained before, like modification can be a bit tough because you have to prove the whole algorithm itself, whereas in reduction, you are just changing your input and using the already proved algorithm to prove it basically. So the timing analysis is also easy in that case. So this is the first, before moving forward, if you have any questions regarding logistic or anything, feel free to ask it. Yeah, we can go ahead. So this is the problem statement. So you are playing a game called Monster Labyrinth, wherein your goal is to navigate through it and defeat the monsters. So the labyrinth is given to you as a directed graph G, and you are given a starting vertex S and the end vertex T. And there will be some subset M of V, which are basically your monster nodes. And these monster nodes are identical for the sake of this problem statement. They're identical, so there is no differentiation between the monster nodes. And if you visit a monster node, you have to defeat it if you want to move forward in that path. And if you return to that monster node again, let's say we have a cycle, then you have to defeat it again in order to move forward. So we have to determine if it is possible to go from S to T by defeating exactly two monsters. Let's take an example to understand the problem statement better first. So this is the graph that is given to us, and we want to find if we can actually defeat two monsters and move from S to T. So what do you guys think? Do we have a path here by defeating exactly two monsters? So the blue ones are your non-monster nodes, and the red ones are your monster nodes. So this is a monster node, this is a monster node, this is also a monster node. So let's say there's one path, this is the path, but you can see like, yeah, so in first path, we can see like there are two monsters that we can defeat. And in the first path itself, we found that answer. Is there any other path that has the same property? I think this has to be the only one, because if we take this one, then we are defeating three monsters. If we go from here to here, there is a cycle here as well. You can see like this is a cycle. This is a cycle here. So you could just move here like within the cycle, but it will be more than two monsters. So I think this is the path S to T, wherein you are defeating exactly two monsters. So in the second problem, in the second graph, I don't think there's any path. So monster itself is one. So in order to defeat two monsters, you need to have at least a single graph, at least one graph. So I don't think there's any path here. So in this case, yes, you have to return true. In this case, you will return false. Did you guys get the example, or if you have any questions, let me know. So graph reduction versus modification. In reduction, you just change your input graph G and you convert it into a graph G prime, and you use the algorithms that you already know to solve it. As I explained before, it is easy to prove the correctness and it is easy to find the runtime. Whereas the modification algorithm, you modify a subroutine in order to solve the problem. So you come up with your own algorithm, or maybe some modification of the already known algorithms that you know. But in that case as well, you have to prove like there may be different cases, there will be a for loop. So we'll have to prove that. And that might be a bit challenging as we saw in the lectures. But I understand it is more natural to think this way, like just come up with some algorithm, but yeah, it has its own challenges. So let's see how we can solve the previous problem using graph reduction. So this involves like, yeah. So what we can do, we can actually try and change this graph into some other graph and convert this problem into a reachability problem. Basically, now we want to traverse the graph, and if it is true, that means we should be able to defeat the monster, or if it's not possible to go from S to T, then it should not be possible. So the modification step involves something like this. So before that, we need to think like when we are traversing a path, let's say we are going from S to T, what do we need to keep track of? So let's say first node is node 1, second node is node 2, so on and so forth. So at every node, you basically need to keep track of how many monsters you have defeated so far. Yeah. So let's say this one is not a monster node, so right now it is 0. And it is given that the starting and the end node is not a monster node. So let's say we are here at node 1, but this is not a monster, so number of monsters will still be 0. In node 2, we have one monster, so this 0 will be incremented by 1. And let's say there is one more monster here, some nk. So it will be 1 throughout here, and suddenly it will become 2 here. Yeah. And if we are able to go from S to T, such that even after reaching this T, we still have 2 monsters defeated, that means we have a path. This makes sense? Yeah. So yeah, so we need to keep track of how many monsters we have defeated so far. So now let's go and create graph G prime. This is where the challenging part is. You need to think actually how you can modify your graph to solve the problem. So we will see like how we can actually modify our graph. So this involves 2 steps. We need to think how we can change our nodes, and then we need to think how we have to modify our edges as well. So this is what I'm going to say. Let's say we have a node V in the graph. So we are basically breaking it down to 3 different nodes now. So if it is, so V0 basically means that no monster has been defeated so far. And V1 will mean that only one monster is defeated so far. And similarly, V2 means we have defeated exactly two monsters so far. So this is the reduction step. We are basically now changing our vertices and edges. So this is how we change the vertices. Let's see how we are going to modify our edges as well. So let's say this vertex V is a monster. So how do we connect the edges now? So let's say we have a vertex V, which is a monster, being connected to some node, other node U. So if it is V0, then we go to U1, right? Because you have to defeat that monster. So till now you only had defeated 0 monsters. So if you want to cross from V to U, you have to defeat that monster, only then you can go forward. So this way, we are actually telling the graph like we have defeated one monster. Yeah? Similarly, if you are at V1, you will go to U2. So till this point, you have defeated one monster, and now in order to move forward, you have to defeat this monster as well. So this is 1 plus 1. Make sense? And similarly, for this node, we see that we already have defeated 2 monsters already. So this should be the terminating node. That means we should not move forward. Because if we move forward somewhere here, it will always be greater than 2. So we don't want that. So this is the terminating node, this V2. And hopefully this V2 is our T2 in the end. And if the vertex is not a monster, then that means like the edges will just stay at the same level. If you had defeated 0 monster, it will be still at 0 monsters. If it was already 1, then you will still be at 1. Similarly for 2. This makes sense? Any questions? Okay, let's move forward. So now let's take an example. This is one of the examples that we saw earlier, wherein the answer was false that we saw. Let's see if our algorithm actually works here. Let's see how we are going to modify this example into our new G dash. So this is a G, and we need to convert it to G prime. I'm interchangingly saying G prime and G dash. Please don't get confused by it. Uh, so yep. So first, what we are doing, we are just duplicating the nodes. So we can see like this first section here is consisted of S naught, 0, S zeros, node zeros. Here we have subscript 2, and here we have subscript 1. So as we saw in this constructing the graph, if we are not defeating any monster, let's say, then we can stay at the same level. So here we basically means we are just connecting them one by one, just as it was in the actual graph. Now comes the monster part. So we know like this C is connected to B. Let's confirm once. Yeah, it's connected to B and D. This is connected to B, and this is D. So we defined earlier, like if it is Ci, it should go to some Bi plus 1. Yeah, if we are defeating that monster. So this one should be B naught, sorry, B1, and this one should be D1. Is it clear? So we basically are saying like this C naught will be connected to this B1 here and this D1 as well. Yeah. Similarly for C1, it can be either connected to B2 or D2. So this will go here, and the other edge will be along this path. It's exactly the same thing. Any questions here? Anything like you haven't understood regarding the edges or nodes? Okay, sounds good. So this is the high-level description of the algorithm. So we are given this input as graph G, which is a collection of nodes and edges, V and E. There is a subset M, basically monsters. So we have some edges, some nodes in that monster subset. And we have these two vertices S and T, which belongs to the nodes. And S and T not equals to monster. So we are first creating a new graph G prime, which will have vertices V prime and edges E prime. And for every vertex V, we add 3 vertices as we did in the previous step. We just first make the copies of the vertices. And for every edge VU of E, if V is not in M, then the subscript remains same. Like if V0 will be connected to U0, V1 will be connected to U1, V2 connected to U2. If V is in monster subset, then we have to increase the subscript. So 0 will go to 1 and 1 will go to U. Yeah? So you, one thing you have to keep in mind, so this V and U, they were originally present in the graph G, and this V naught, U naught is a part of new graph, your G prime. And then what we do, we explore, we use any of the graph search algorithm, maybe BFS or DFS, and we start from vertex S naught, and we check if T2 is visited. If it is, then you return true. That means you can go from S naught to T2, and the subscript basically tells you how many monsters you have defeated till then. Any questions in the algorithm? Okay. So let's see if our algorithm actually works on the test example. So we start with this S naught, and we can see like everything here is reachable in this first green box. So we go from C naught to B1, and here as well everything in this B is reachable. And our goal is basically to go from here to T2. So as we can see from this green box, the second green box, there doesn't seem to be any way to this graph here. So I don't see any path here. So that means it is actually returning false. It is exactly what we were expecting, right? So how do we prove it now? So it is that if and only if kind of proving technique that we are going to use here. It's a bidirectional proof, so you need two things here to prove. First one is the forward direction, and the second one is the backward direction. And you cannot miss on any of these two. It is very important to have both of them here because it is if and only if kind of proving technique. So we define a forward direction first. So we are going to say if it is possible to start from node S and reach node T while defeating exactly two monsters, then we return true. So the backward direction will be if it is possible, if it is not possible to go from S to T, it should return false. Yeah. And the contrapositive of the same, this backward direction, would be if the algorithm returns true, that means there is a path from node S to node T by defeating exactly two monsters. So the idea here is basically if A implies B, if you want to prove this, you can prove it using a contrapositive by saying like not B implies not A. If you look at the truth table of this, they are exactly the same thing. Any question here? Anything confusing in this part? Okay. So let's try and prove the forward direction first. So let's assume that there is a path from S to T in our graph G that involves defeating exactly two monsters, and we want to show that the algorithm actually returns false. So what does this path look like? So let's say we have a path something like this. We are starting from node S, we are going till node T, we have intermediate nodes from A to G, and this node C is basically a monster, and this node F is also a monster. So it will look something like this. In a path, you will exactly have two monsters there. So now, if we convert this path into a G prime, then we will see something like this here. So for the first, so let's say all the nodes till the first monster will have a path like this, right? Because till this we haven't defeated any monster from S to C. And this will be in G prime because all the nodes are non-monster nodes. So on the bottom you can see like there's a path from S naught to C naught. So at this monster node something different happens. Basically we are jumping to the next subscript. So now as you can see here, we are jumping from C0 to D1. And by the definition of our graph, there is an edge from C0 to D1. So this is also a valid thing. This is what happens. Now let's go and see what happens after D. So from D till F, you will have the same subscript because you are not defeating any more monsters between this block. So the subscript will stay as 1 here, as you can see here. Similarly, towards the right of this F, we are defeating this monster F. That means we have to go from 1 to 2. So now the subscript is 2. And all the nodes towards right of this node will basically have subscript 2 only. And we can see like we are able to reach node T2. Yeah. So we started from S0 and we are reaching T2. So basically we are saying there is a path in G prime from S0 to T2 if there is a path in G itself. So the algorithm will return true in the end. Is it clear? Any question? Like if you have any question, how you should answer in the homeworks or maybe your midterm, something like that. Anything that is ambiguous. Okay. So now we proved the forward direction, we need to prove the backward direction as well. So in the backward direction, the contrapositive version of that, we said like if the algorithm returns true, then it is possible to go from node S to node T by defeating exactly two monsters. So let's say the algorithm returns true. So the first half we generally assume, and then we show like the second half is also true. So let's say the algorithm returns true. So what must this path look like? So let this path be something like this. Yeah. So we are going from S naught, A naught, B naught, C naught, and somewhere we found one monster. And at this point, so this is C naught is basically a monster. It will jump onto the next subscript from C naught to D1. And then we found the other monster at F node. So we are jumping from 1 to 2 here. And when we reach this node T, we will have a subscript 2. That means we defeated 2 monsters. And we can say this, it is true because there are no edges where we are jumping from a higher subscript to a lower subscript. Like you saw, like while we were formulating our graph G, we are always going from I to I plus 1, or we were staying at the same level, I to I. So it doesn't happen. So that's how we can say, like, yeah, this is one thing. So mathematically, basically, we are saying if there is a node from V to U, you stay at the same subscript. This X is basically the subscript, which is basically either 0, 1, or 2. So you can stay at the same subscript, or you can jump onto the next one. But if X is already 2, then you don't go to X, then you don't go to X plus 1, because this is a terminating node in itself. Clear? Any questions in this one? So that means we are saying if the algorithm returns true, that means there is a path from S naught to T2 by defeating exactly 2 monsters. So this is interesting, the runtime analysis. So we have 2 parts basically. First one is constructing the graph G prime itself, and then second one is running your explore algorithm. And while creating the G prime, we found out like we have 3 times the vertices in G prime, because we are dividing every node into 3 different nodes, 0, 1, and 2, with subscript 0, 1, and 2. And for every edge VU in G, there are at most 3 edges. Yeah. So in case of monster node, we only have 2, but if it is a non-monster node, then in that case, we have 3 edges. Yeah. So if you have something like V to U, so in our new graph, you will have V0 to U0, U1 to U1, V2 to U2. Yeah, you cannot have more than 3 different edges. So we are saying like creating this graph, it takes this amount of time, which is basically 3 times the vertices plus 3 times the edges. So the overall runtime asymptotically will be equal to O of V plus E. And the second part is running our explore algorithm on G prime. So we know like the explore algorithm, it takes a linear time, which is O of V plus E. And if you add these 2 things together, it will still be O of V plus E. Is it clear? Any question in the runtime analysis? Should we move forward? We can take one more example. Before going to this problem, I want to ask again, if you have any questions, do let me know. I will be more than happy to answer your questions. Anything that wasn't clear enough, or there was some ambiguity, anything like that. Okay, so if you are able to see it in your homeworks, you should be able to do it now. If not, then feel free to reach out to any of the TAs or professors. Yeah. Or I will stay here after class for a couple of minutes. You can ask me then. Okay, let's go to the second problem. Let's say we have a directed graph G, and we want to determine if there exists a vertex V such that for all vertices U that belongs to the graph, there exists a path from V to U. So basically what we are saying, let's say there is a vertex V, and there are some other vertices U1, U2, U3, U4, UN. We are basically saying we want to see if there exists a vertex V, like it should be reachable to all the other vertices. There should be a path from all the U's here. Is it clear? So the question is to find this thing, this node V. So let's see an example here, and let's see if we can find something like that here in this example. So let's check for node S. So yeah, you can visit A. So let's just make a set of all the nodes that you can visit from node S. So A can be visited. Similarly, B can also be visited through this path. D can also be visited from B. T as well from D. And you can also go to this C. I think we only have 5 nodes. So yeah, so actually C, luckily the first node that we chose was the answer in itself. So yeah, we have a node S which is actually reaching all the other vertices. We can take some interesting example here. Let's say we don't have a, let's say we take some other node which might not be reachable to, yeah, there's a simple example here. Yeah, let's say we start with node C. Now let's make a set of all the nodes that are reachable from here. So we can go to B from here, but I think that is the only node that we can reach, right? Any other node is oh, okay, no, I'm wrong. Sorry, I think we have a couple of more answers here. So from B we can go to D. From D we can go to T. Anything else? I guess this is it. So we are not able to reach S or A in this case. So this cannot be our answer. So yeah, so we need to find this node S. So let's see how we can do that. So yeah. So I will give you an algorithm and we will see like if it is actually solving the problem, and we will do some analysis and correctness proof on that one. So this is our input graph G having vertices V and E. For each vertex V in this graph, we are running the explore on that particular node. So we are iterating over all the nodes separately, and we are running explore on those nodes. And if all the vertices are visited, then we return true. Otherwise, if for any of the nodes we are not able to return true, then we will return false. So the question is it actually solving the problem? So we can come up with an algorithm, but it doesn't solve anything for us until and unless we can prove it actually works. Yeah. So let's go over the correctness proof. So the same stuff that we did in the last problem, bidirectional proof, forward direction and the backward direction. We will prove these two things separately, and yeah, that will be the end of the proof. So the first part is the forward proof. So we are saying if there exists a vertex V that can reach all vertices in V, then the algorithm returns true. Similarly, for the backward direction, if the algorithm returns true, that means there is a vertex V that can reach all the other vertices. Is it clear? Like how we are coming up with the forward and backward directions? This is going to be very crucial going forward when you will solve your assignments or yeah, any other questions. Okay. So let's follow the same strategy that we did last time. So let's assume like there is such a vertex V that exists. Yeah, first we start with some assumption, and that is mostly the first half of the forward direction that we have stated. So let's assume like there is a vertex V, then then when the algorithm runs explore G and V, it will be able to visit all vertices in the graph. And since there is a path from V to all V's, therefore the algorithm returns true. So this is quite kind of intuitive. Let's say we choose a vertex V and it is able to reach all the other vertices. So based on our algorithm, we can see like it is actually returning true to us, right? That is what we wanted. So this is a very straightforward, and we also expect you to, like if the problem is like this, you can just give a high level proof like this one. It doesn't require to go into too detail. Similarly, for backward direction, we are assuming, let's say the algorithm returns true. So here we are assuming like it returns true already. That means that there is some vertex V that explore graph G and vertex V can visit all the other vertices. So basically, if it is returning true, that means we have found a vertex V that is actually going to all the other vertices. Let's go back to the algorithm. So we are saying, like, if the algorithm is returning this true, that means for some V that belongs to this capital V, there is one solution, and after running the explore on that particular node, we are getting true. So this is actually the definition in the algorithm itself, and yeah, this is how the explore algorithm works. So therefore, a vertex V can reach all the other vertices in V it actually exists. Yeah. One interesting thing to note here is that we are able to make this strong claim here because we are exploring all our search spaces. Yeah. Because you cannot have any other nodes apart from this set V, right? So that's why we are able to make this claim. So let's do the runtime analysis of this algorithm. Before moving forward, I want to ask any questions here? Yep. Let me repeat the question. So the question is, so do we need to keep some kind of array like to mark visited or something like that? You visited. Yeah. So actually, this is a part of your this explore algorithm. So we are not actually. So you can use any of the algorithm. So if you use BFS or DFS, you know you need to keep track of the nodes that you have visited. So that will come into this second statement. So right now, for the sake of this algorithm, since we are using reduction, we are not creating a new algorithm. We are going to create the same algorithm that we know of. And yes, you are right, in DFS, we do need to keep track of the nodes that we are visiting. Yeah, and if needed, we reset it. Yeah. Yep. So, sir, can you speak up a bit? Yeah. So let me reiterate. So reduction basically means we change our graph G to some graph G prime. So basically we are changing our input and we are still going to use some already known algorithm on top of that. So it is a reduction. So if you look at here, we are still using some known algorithm explore GV, but yeah. So the only thing that we are doing extra here is basically we are checking all the vertices. So it is basically a reduction. Yeah. Anything else? Okay. Yeah. Yeah. So let's do the runtime analysis of this algorithm. I think we still have 26 minutes to go. So yeah. Do you want to guess the runtime analysis of this one or give your reasoning? Yeah.
So I went back to the explore algorithm and it goes through every edge. So I'm guessing it's going to be linear, but then it's for every vertex. So I don't know. I guess there's like a V and E which are both linear, so that might make it more tight.
Yeah, you are actually you are on the right track. So as you said, this explore algorithm, it is linear algorithm. So it will be V plus E, big O of V plus E. And the second part that you mentioned, we are doing it for all the vertices, right? So this is the big for loop outside. So we are basically saying it is V multiplied by big V plus. Yeah. So yep. So V into V is V square and the other term. Is the runtime analysis clear?
So I'm just not sure why in the slide it says V squared plus V. Like how would this be V times V plus E?
Yeah, so it is basically V times V plus E. So you just remove the bracket, so it becomes V square plus.
Okay, I forgot I did all that.
It's fine. Yep. Yeah. It doesn't look that good to me. We have a V square term. So I think we should be able to do better. After all, we are learning design and analysis of algorithms, so we need better algorithms to analyze. So let's see if we have other solution. Or like I would like to ask you guys if you think you have another algorithm that can solve it in less than this time. Okay, so I will propose an algorithm and then we will go over the correctness and the runtime of that one. Uh, so before going forward, I just want to know if this pre-order and post-order is already covered in the class, or I need to go over it again. Is it covered in class? Yeah. Okay. Yeah. So this is how the algorithm goes. So similarly as before, we have our input graph consisting of node V and edges E. So first we run the DFS on this graph. We can choose any of the vertex to our DFS, and let H be the vertex with the highest post number. Yeah. This ringing some bells from the lectures, like the node with the highest post number. Yeah. So we do this one, and the second step basically says, now we know the node H, so now we just run a simple explore on that node, and if all the vertices are visited, then we return true, otherwise we return false. A very straightforward algorithm, right? Just a two-step algorithm. So this is the beauty of reduction. You don't have to go and create the whole algorithm itself. You just piggy bank on the other algorithms. Yeah. So let's see an example here. So let's do the post order numbering for this graph first. And for the sake of simplicity, we will do it alphabetically. So we will start with node A first. So let's do it. Yeah. So we have node A here. We will give it pre number 1. Then we will go to B. This will be 2. Then we will go to D. This will be 3. Then we go to, where do we go after this? We go to C. This will be 4. Can we go anywhere else from C? I think this is a dead end. So this is our first post order number here, 5. Then we go back to D again. From here we go to T. The pre will be 6. So this is a last node. We cannot go anywhere from here. So the post will be 7. We go back to D again. From D we don't see anything else. So, or do we see anything? No. So D post will be 8. Then we'll go back to B again. Is anything possible from B? No. So this will be 9. We will go to A again, and all the nodes are visited that it could visit. So this will be 10. Are we done? So we can see like the S is still not visited. So we will have to do it for S as well. So we start with S. We see like the node A is already visited here. So we don't do anything. This will be 11 pre and the post will be 12. Got it? So yeah, this is exactly the same. So if you remember, in order to get the post thing, we basically did DFS, and then in that fashion we just chose the pre and post numbers. Yeah, is it clear? Any questions in this algorithm? Okay. So this is something interesting. I really like this proof. So similarly, like the previous problems, we have forward direction and the backward direction. In forward, we say if there existed vertex V that can reach all the other vertices, then we return true. And in the backward one, we say like if the algorithm returns true, then there exists a vertex V that can reach all the vertices in V. Yeah. So the proof goes like this. So I think the backward proof is much easier than the forward proof. Because in backward proof, let's assume the first half, let's say it is actually returning true to us. So what happens? What does that mean? So this means that when we run explore G and H, where H is the vertex with the highest post number, all the other vertices are getting visited. So that means we do have a vertex V, which turns out to be vertex H here with the highest post number. That means, yeah, so there exists a vertex H. Yeah, so this means this backward direction is true. So the backward proof you can see is very easy here. But the forward is something non-trivial here. So we need to show like there actually exists a vertex V. Yeah. So let's see how the proof goes. So assume like there exists a vertex V that can reach all the vertices. Let's say this is a vertex V from where we can go to any other vertexes. And we want to show that there is a path from H to V. So understand the distinction between H and V here. So V is basically the one which is from where we can go to any other vertices. And H is the one with the highest post number. And our goal is to basically say like H is the one that is able to reach all the other vertices. Yeah. Is it clear or is it a bit complicated? So we are just defining stuff now. We are not doing anything. Any difference, any confusion between H and V? Okay. So if you remember, if you can recall from the lecture, if a vertex H is the one with the highest post number, then what does it mean? Anyone remembers that? Yeah, exactly. So that means that the vertex with the greatest post number is basically it belongs to the source SCC. Yeah. So this is important. So we are going to use this in our proof. So we are saying that the H is in the source SCC. So now we know that the H is in source SCC. What does this tell us about the SCC that V is in? So now we have sorted out H, we need to do something to V as well. So we are saying like the V is the one from where you can go to any other vertices, right? So can we say V is a source, V is in source SCC? I think we can say that safely because we can go to, source is basically where like it will only have the outward edges from itself, right? It won't have any incoming edges. Yeah. So we can safely say like since V is able to go to any other vertices, it should be in the source SCC. And the second is now we need to prove like the SCC that V is in, it is the one and only source SCC. Well, you will come to realize why we are actually doing that. But do you want to take any guesses like why this is defined this way? Why do we need the second statement? So the first one is first one is very trivial. We can see that it is in source SCC. But why do we need it to be the only SCC? Okay. Yeah. Uh, because we want to show that the vertex V is reachable from our highest post order number vertex. Because if we are able to show that, that means like since H is able to visit V, we should be able to visit all the other edges as well, right? Because we said like we said like V is something that can go to any other vertex here in the graph G. Yeah. And we want to show like this post number H, it can go to V itself, or let me change it this way because H itself is part of G. So we are saying like this H can go to V. So following the path, we can safely say like if H is able to go to V, then we should be able to go to all the other vertices because of the property of V. Understood? Is this clear or you need more clarification here? Okay. We still have 5 minutes. Yep. Uh, so let's say first we're assuming like let's say there is a vertex V that is actually reachable to all the other vertices, uh, and let H be the one with the highest post number, and we are going to prove this by contradiction. So we are going to say that there is no path from H to V. So let me make a small graph here. So we are saying there is no path from H to V. This path doesn't exist. Yeah, this is the assumption. And therefore, if H and V are not reachable from one another, or basically if V is not reachable from H, then the least thing that we can say for sure is that they belong to different SCCs. Yeah, because if H and V, if they belong to the same SCC, by the property of SCC, we can say like there has to be a path from H to V. So we can safely say like there are two SCCs. H belong to one of them and V belong to the other one. Clear? Yep. So yeah. So we are saying this is. So we know like this is a source SCC. Yeah. So now we know that there is a path from V to H because that's how we defined our V in the first place. So we know like there is a path from V to H here. But we are assuming like there is no path from H to V. So this implies, and we also said like this H has to be in the source SCC. So what we are saying here is like if V is reachable from H, if H is reachable from V, then it cannot be a source in itself because there are some other nodes that are coming to it, right? Source basically means that it should not have any incoming edges. It should only have outgoing edges. But there is one SCC that V belongs to, which is going back to the node edge, the SCC having node edge. So we are basically contradicting our this thing here. So basically this cannot be true because this assumption of ours is getting cancelled now. Because if we say like there is no path here, then this cannot be a source one because we do have a path from V to H here. So basically you can say this assumption here is false. So the assumption that we made here, that there is no path from H to V, it is not right. So therefore there must be a path from H to V. I know it can be a little bit complicated to understand it at first, but go over it again and let me know if you have any question in this one. Is it clear? We have this. So yeah, it should return true. Yeah, this is the same thing that I said earlier. Because of contradiction, there has to be a path from H to V. So let's do the runtime analysis. So the first step, we were doing the DFS to calculate the post order numbers. And then we find this vertex H and then we again run this DFS. So the first DFS is O of V plus E, and the second DFS that we start from vertex H, it is also O of V plus E. So asymptotically it is equal to O of V plus E. It is nothing but the addition of these two terms. Yeah. If you have any question, like I can go over this proof again if you want. This contradiction, if it is not clear to you. Thank you guys, and I will be here for a couple of minutes. If you have any question or anything, yeah, feel free to ask. I like it. Teaching is kind of fun. Where does it close from? Okay. You came early or what?
Huh?
You came a bit early.
Yeah.